Okay, now we're going to address a thing we call the expectation value. And the expectation value really means if you measure something, what value do you expect? What value do you expect to measure when you make a measurement of some quantity? And what it really is what is the average value of some measurable quantity for a quantum system with a certain wave function. Now, as an example, let's ask the fairly simple question: what's the average momentum for a particle in a box? Well, it's stuck in the box, so the average momentum has got to be zero, right? It isn't the particle isn't going anywhere. It's stuck. If it had an average momentum, it has to have an average velocity. If it's got an average velocity, then on average it's going somewhere, and the darn particle is stuck in the box. So the average momentum has got to be zero. It simply can't have it. There's no other possibility. So let's check this thing out and see if that's true. For the particle in the box, the wave function is the square root of 2 over L times sine of n pi over Lx. And what we did last time is we took that and we expressed it a different way, right? We turned that into square root 1 over square root 2 times 1 over I times 1 over the square root of L times e to the I n pi over Lx minus or plus 1 over root 2 times negative 1 over I 1 over square root of L e to the minus I n pi over L times x. And again, that first bit there is psi, or phi plus of x, and the second bit there is phi minus of x in the nomenclature we've been using. And then those 1 over root 2's are the real parts of the coefficients a plus and a minus. So this is just 1 over root 2 times 1 over I times the function phi plus 1 over root 2 times minus 1 over I times phi minus. So the average value of P we express with these, the greater than and less than, the angle brackets that we're going to use a lot of in this class. So one of the things that can mean is an average. And if we surround a measurable quantity with the brackets like this, that means an average. And that's actually quite a general indication. So if you see that that symbol, that often means average in mathematical notation. So the average momentum, again, that's what we call the expectation value of the momentum, just equal to 1/2 the value of the momentum for the phi plus eigenfunction of momentum plus 1/2 the value of the momentum p minus for the eigenfunction phi minus of the momentum, because those 1/2s are those coefficients a plus and a minus squared. So that is 0, right? Because p plus minus is just plus minus h bar pi over L times n. So 1/2 of the positive value plus 1/2 of the negative value, 50% chance of finding the positive value, 50% chance of finding the negative value. So if you shake the system up and just say go measure and say on average what do I expect to find, the answer is 0. But you don't find 0 by ever measuring 0. You find 0 by measuring plus h bar pi over L n half the time and minus h bar pi over L times n the other half the time. Think of the particle as bouncing back and forth in the box with a certain amount of total energy, a certain constant magnitude of momentum, but it's continually switching directions as it bumps into the wall. It makes a great deal of sense in this case, but it's also a very generalizable concept. This is generalizable, so let's go ahead and generalize it. The general way of finding the expectation value is pretty straightforward. So we're going to write the expectation value of some observable, and that's our little O with the tail on it, is just going to be the sum of all those amplitudes a sub j squared times the value of the particular value of the observable Oj for a given wave function. That way, this is simply a weighted average of these observable these observable eigenvalues that comprise the expectation value. So just to be clear, the wave function, the overall wave function, is this linear combination of coefficients C1, Phi1 plus C2, Phi2, etc., which in general we can write as a sum over some index value j, which is going to be all of the quantum numbers in the system, in this basis set for this particular observable. So the sum over j of the coefficient Cj times the basis function phi j, and also the amplitude Aj is just the real part of that coefficient Cj. Now the sum of those amplitudes Aj squared is going to be 1. That's part of the normalization. We'll get into that more in a little bit, but that's always true, and that's essentially saying that the probability of measuring something, some value, when you go to make a measurement is 1. The total probability, just like with the measurement in space when we normalize the wave function. It always boils down to the probability that you're going to find something has got to be 1. Finally, remember this: the operator O, big O with the hat, operating on the basis function phi j, is going to spit out the observable little o sub j times that basis function phi j. So that's the eigenvalue representation, the eigenfunction representation of the system that guarantees that in fact we do have a set of eigenfunctions for this observable, this particular observable O, whether it's momentum, whether it's energy, whether it's position, whether it's favorite musician, whatever it is that's observable, that's always a characteristic of the system. Okay, so now here's an interesting thing. If the wave function is an eigenfunction of the Schrödinger equation, okay, so H phi sub j is equal to total energy of eigenvalue of j, E sub j times phi sub j. So it's an eigenfunction of the Schrödinger equation. And the overall wave function is a linear combination of that basis set of eigenfunctions of the Schrödinger equation of total energy. So that wave function psi is equal to C1 Phi1 plus C2 Phi2, etc., etc., etc. Then if you measure the energy with some probability, and that's going to be the square of those coefficients, right? So if I measure Ej, the probability I get that answer is the real part of Cj squared, or Cj complex conjugate times Cj, or in our bracket notation, we have Cj bracket Cj. That's the probability that I will measure a specific energy, which is a specific eigenvalue of the Schrödinger equation. Whatever the system, but we'll think about the particle in the box in a second. Now I go away, and I come back and I measure energy again. I'm going to measure that value Ej with 100% probability. I'll get the same value again. This is an example of what we call quantum collapse. So when I go to measure the energy of this particle in the box, I have to interact with it. And the act of interacting with it about energy puts it into that eigenstate. It's just like it's actually really a lot like humming a note to figure out if you're in tune or not. And if the note of the box is some complex tune, and I try to figure out how much of it is la, some perfect note, then, not that I can sing perfectly, but then I'm going to take the particle in the box and essentially pull out that one note. I frequency lock to that one note, if you will. I lock it in to that given wave function. So here's how this plays out for a simple example. Let's imagine that I have a wave function psi is 1 over root 2 times phi1 plus 1 over root 2 times phi2. But this time these phis are a basis set of energy eigenvalues, of total energy eigenvalues, the solutions to the particle in the box, so that h, the Hamiltonian with the hat, h phi sub j is equal to total energy E sub j, phi sub j. That's the Schrodinger equation. So the phis are eigenfunctions of the Schrodinger equation. Well, first of all, here's what the wave function is going to look like. Here's our x-axis from 0 to L. Let's make a couple more of these because we have 3 functions to worry about. So the first wave function, phi1, is going to look about like this. It's 0 outside of the box, and it's a sine function inside the box. So that's our favorite ground state wave function for the particle in the box. Phi2 is 0 outside of the box. It's got a node right in the middle of the box, and then it's a full wavelength of a sine wave function. It goes through 0. It's got one node. It's got more than the 0 nodes of the ground state. It's higher energy. Do all the node counting. It's got more curviness, and it's got more total energy. But our overall wave function is a linear combination of these two, and let's look at how this plays out. Over here, sort of at the left quarter, both phi1 and phi2 are fairly large and positive. Phi2 is at the maximum, phi1 is reasonably big. So the wave function is going to be reasonably large and positive over there. If we go right to the middle of the box, phi2 is a node, so it isn't adding anything, but phi1 is nice and big. So the wave function is still going to be fairly big. And it's only when we get over here, sort of some distance toward the right-hand side of the box, that phi2 is negative by some reasonably large value. Phi1's come down a little bit from its maximum. And so that's where we're going to find the node now in the linear combination of these two functions. So it's going to look something like this. It's 0 outside of the box. It's going to have a big positive value on the left-hand side of the box. It's going to go through 0 somewhere in the right-hand side of the box and then have a modest negative excursion, because over there in the right-hand side, phi1 and phi2 are kind of pulling against each other, and so they don't exactly cancel out, but the value is much less. And you really, really should think of something like an sp hybrid orbital when you look at this, because that's we're going to find out is exactly what's going on when we make hybrid orbitals to construct molecules. So now the energy of this E1 is just going to be h bar squared pi squared over 2ml squared times 1 squared. So we don't see that. E2 is going to be h bar squared pi squared over 2ml squared times 2 squared, which is 4. So then when we go to get the expectation value of the energy here, we're going to take h bar squared pi squared over 2ml squared, it's always there, and we have a half times 1 plus a half times 4, because the half is the square of those two coefficients, which are each 1 over root 2. 50-50 chance of the 1 answer, 50-50 chance of the 2 answer, of the 4 answer, n equals 2 is 4. But you add them together like this to get the expectation value. So that's h bar squared pi squared over 2ml squared times 5 halves is the average energy of the system. The cool thing is what happens when we have a whole lot of these. So imagine we have Avogadro's number of boxes, and the wave function in each box is the same as we just went through. So the wave function psi is 1 over root 2 times phi1 plus 1 over root 2 times phi2, and I'm going to use these colors to help distinguish this here. Okay, so let's draw Avogadro's boxes. I kind of give up at 7, but you know, there's a lot of them, right? And in each of these boxes, the particle is prepared in this wave function psi. And don't really worry about how you prepare it. As the instructor, I have sort of godlike qualities, and so I can just do it. Okay, it's done. We have a bunch of these composite wave functions, linear combination wave functions here in this box. Now we go and we measure the total energy, Avogadro's number of times. And the expectation value says that we're going to find 50% in E1, 50% in E2. Those are the square of those two coefficients there in the wave function. And the overall average energy that we're going to get is 5 halves the ground state energy, 5 halves h bar squared pi squared over 2ml squared, as we just found in the previous one. So I do that. Here's Avogadro's number of boxes, And basically, some of the time I get phi1s, let's put them in those boxes, and some of the times I get phi2 I get the eigenvalues of those for the energy, but I also put each particle in each of those boxes into that eigenvalue, the eigenfunction of the Schrodinger equation, okay? So instead of being in the wave function psi, now these things are caught in the wave functions v1 and v2 as shown. So now time passes, and I go measure them again. And I'm going to measure, here's my boxes, exactly the same thing. So in each of the boxes now I know with certainty what energy I'm going to find, and the problem is done. Now the reason that I've been careful to specify that this is true for eigenfunctions of the Schrodinger equation is there's one little messy detail, and that's time passes. So there is a time evolution that's present in this, and since we're dealing with the time-independent Schrodinger equation, to be correct about this, we have to be a little bit careful. So if the wave function is a wave function, an eigenfunction of the Schrodinger, or linear combination of eigenfunctions of the Schrodinger equation, then this holds quite strictly, and I can say it without kind of losing sleep at night over having kind of made a mistake. If in other systems, if I go and measure a quantity that isn't total energy, something else, then right after that measurement, I know with high precision what the wave function was. But it has a chance of wandering away from that value, because if the measured function is not a valid solution of the Schrodinger equation, it's not going to be time independent. So there's going to be some time evolution, and we're not really dealing with that right now. But the general concept of quantum collapse is that for at least a while after you make the measurement corresponding to a given eigenfunction, the system is in that eigenfunction, or something that looks a lot like it. In this case, where the eigenfunction is an eigenfunction of Schrodinger, then a while is forever, and it stays like this here. But that's the concepts of quantum collapse, that you change, you resolve the probabilities, is extremely important, and it's actually the issue behind what's called the Copenhagen interpretation of the wave function. There's metaphysical details of that have been at the heart of quantum mechanics since the very, very earliest days.